Welcome back, everybody. So today we're going to be finishing up our discussion of universality. And in particular, what we're going to be doing is we're going to be showing that the two-level rotations that we covered in the last lecture can be used in order to be able to synthesize an arbitrary unitary. So let me share my screen so I can go through how the construction works. The basic idea behind the construction is that what we want to do is assume we're given some arbitrary unitary matrix U. What we would like to do is we'd like to be able to find a bunch of two-level unitaries where recall that two-level unitaries take the form 1, A, B, C, D, 1, and 0 everywhere else. So basically, what ends up happening with a two-level unitary, this is just an example of one particular one. What this will end up doing is it'll do a rotation or a unitary transformation inside the block spanned by the 1 vector and a 2 vector. But it acts as identity on 0 and the 3 vector. Okay? So this is the idea. There's one particular subspace spanned by 2 vectors. In this case, it's 1 and 2, on which a two-level unitary will apply a given transformation. And on everything else, it will apply the identity transformation. Okay, so that is what we showed how to construct it. And the way that we constructed it, if you recall, is we took this particular subsystem over here, or subspace, and we mapped this to an ancilla qubit. And then we applied a controlled unitary to qubit. And then by applying the controlled unitary to the qubit, that was logically equivalent to us applying this transformation to the two-dimensional subspace. And by mapping back to the original basis, this transformation ended up allowing us to apply a rotation in an arbitrary two-dimensional space. But for the purposes of this lecture, the precise construction that's used in order to build the two-dimensional rotations kind of ain't that important. The thing that really ultimately ends up mattering is that we've got a scheme such that for any specified M and N, as well as a unitary transformation U, this two-level unitary will map A M plus B N to some unitary transformation of it that will look like the following. It will end up being B U 1 1 N plus B U 0 1 N M plus A U 0 0 M plus A U 1 0 N. Okay, so basically what it's doing is it's just applying this unitary, which I've defined here as just a 2x2 matrix containing the elements U0 0, U0 1, U1 0, and U1 1. And we're applying this arbitrary unitary matrix just to this subspace over here. Okay, everywhere, every other vector, like a vector L, not in the span of M and N, will be mapped to L. Okay, so that is the basic action that the two-level unitaries end up taking. And what we want to do is we want to find a sequence of these two-level unitaries that ends up doing the following. We would like to be able to find a sequence that's of the form W1 down to Wn, such that these unitaries acting on U equals the identity. Now, because the product of unitaries is itself a unitary, we end up having that this is a unitary matrix here. And therefore, because the product of this matrix and U is identity, we have that W1 through Wn has to be the matrix inverse of U, which is equal to, because U is a unitary matrix, the Hermitian transpose of it. And this ends up implying that this is equal to Wn transpose, or conjugate transpose, down to W1. Conjugate transpose is equal to U. So by finding the sequence of W's that when multiplied together, where W's are the two-level rotations that are unitaries that we're dealing with, these W's acting on U, if we can find the ones that make the identity, then the adjoint of that sequence will actually have to be equal to U. So that shows you how we can actually construct an arbitrary unitary by decomposing it into those two-level rotations. But to give you an example specifically about how this can work, let's actually just go through a worked example, okay? All right, this is being a little bit more general, perhaps than some of you might like, so I apologize in advance. But let's say that our unitary ends up looking like this, where A, B, all the way down to I are all real numbers. I chose real numbers because of the fact that I want to be able to break this into concrete gates. It turns out if they were complex, then it's very difficult for me to give a closed form expression for what the unitaries actually are. But in the case where they're all real, it's actually pretty easy. So let's imagine this is our transformation, and I promise you that whatever these A, B, C's, and D's are, these are unitary matrices of size 3 by 3. So that is the these are the individual matrices that we want. Now we can ask ourselves, well, all right, well, what does this matrix end up looking like? Well, this matrix ends up being of the form A 0 0 plus B plus B, let's see about this. Will map to 1 and then 0 over there, yeah, plus C 2 0, plus so on and so forth. So what my aim is going to be as the first stage of this is to do these two-level unitaries in order to make both of those matrix elements 0, because of the fact that I want to turn this matrix into something of the form 1 0 0 0 0, and then I don't know, E prime, H prime, F prime, and I prime down here. So I'm going to begin by zeroing out the elements of the first column. All right. So first step, what I need to do is I want to zero out. First, I guess I want to zero out the B entry. And so we can view this as trying to find a unitary U dagger that will map A 0 0 plus B 1 0. We'd like that to map to the some new value A prime, or actually, I guess we can view this more specifically, is we'd like this to map to absolute value of A squared plus absolute value of B squared 0 0. Okay, so this is actually equivalent, just by taking the adjoints, this is equivalent to saying, all right, well, I'd like U dagger acting on A 0 plus B 1 0 equals, I'll just put like extra big brackets around here to be clear what I'm doing, equals square root a squared plus b squared, 0, 0. Okay, so just by looking at this, that's equivalent to saying that I want u dagger a0 plus b1 divided by square root of the absolute value of a squared plus absolute value of b squared, acting on acting on this state is equal to the 0 state. And this is equivalent to saying that I want u acting on 0 equals a0 plus b1. Yeah, you see now why I called it u dagger, because I knew that I was going to have to take an adjoint in the end. So knowing this in advance, I would like to find a unitary matrix U that ends up doing this. Now, if A and B were both arbitrary complex numbers, as I mentioned before, this would be difficult to be able to find the particular unitary. Although we could do this using our single qubit universality result. But we might have to go through a brute force calculation to be able to find an appropriate unitary for it. But if they're real valued, this actually isn't that hard. So the way that we can do it for a real valued matrix is we can use the fact that Ry of theta is equal to e to the negative I y theta over 2, which is equal to cosine of theta by theta by 2 identity minus I y sine theta by 2, like this. All right, and so now if we see the action of this operator acting on 0, well, we end up seeing Ry of theta acting on 0 is equal to cosine theta by 2, 0, minus I y sine theta on 2, 0. And recall that the y operation is equal to 0, negative I, 0. So therefore, this is equal to cosine theta by 2, 0, minus I sine theta by 2, I times 1. Now the I and the minus I cancel. And so this is just cosine theta over 2 plus sine theta over 2. And what we would like this to be equal to, in our particular case, is we'd like this to be equal to A0 plus B1 divided by square root of A squared plus B squared, which again is a unit vector. So a solution to this will exist. The solution is actually really obvious. The solution to this is just theta is equal to 2 arc cosine of A divided by square root A squared plus B squared. Now, if we plug this into the expression, we can see that, well, 2 cancels the 2 here. The cosine cancels the arc cosine, and we're left with a coefficient of A divided by square root of A squared plus B squared. Similarly, when we put this into the sign and use our trig identities, we end up finding that that coefficient ends up becoming B. So this angle over here actually does everything we need. So now going back to our original formula that we have here, what we're going to want to do is we're going to want to pick our first rotation, W, I don't know, N, I'll call it, to be equal to the two-level rotation that will take the form. It'll be a two-level with U equals Ry of 2 arc cosine of a over square root of a squared plus b squared. And the two levels, which I called m and n previously, with the first level m equals 0, and the second level n equals 1. And we saw the construction to do that. So in any case, what we'll get when we carry out this rotation is we'll end up getting A, B, C, D, E, F, G, H, I. This will end up mapping to square root absolute value of a squared plus absolute value of b squared, 0, c down here, and some other elements that we didn't compute. So I'll just call them e prime, f prime, g prime, h prime, I prime. Some of these actually won't be changed from their original values, but these are the particular, but I've just used primes in order to reference each of them. So we've zeroed out the first element. Now we can divide and conquer between these two. Doing the exact same thing, we want to take, okay, well, our next one will be Wn minus 1 to be a 2-level unitary with u equals the ry of twice the arc cosine of square root absolute value of a squared plus b squared divided by the square root of absolute value of a squared plus absolute value of b squared plus absolute value of c squared. Okay, and this just ends up coming in using the same Pythagorean argument that we ended up using before. When I figure out the length of these two to find the appropriate normalization factor, that is square root of the square root of a squared plus b squared all squared plus c absolute value squared, which when you factor this through is just the square root of a squared plus b squared plus c squared. When I go through that step, I end up finding that our matrix, which was of the form square root of a squared plus b squared plus c squared, 0, and c with some other junk over here, we'll end up going to some final matrix element. I'll call it a double prime. These will be zeroed. This would be d double prime, e double prime, f double prime, g double prime, h double prime, and I double prime. Great. So after doing these two operations, we've zeroed out the first column. Now, because this element is real, and actually because I ended up choosing it to be positive for this, because the cosine of these numbers is going to end up giving us a positive number if we choose this, right? This value over here has to be 1, or at least up to a global phase. We can pick it to be 1. The reason why is because every column is a unit vector. And the reason why that has to be the case again for a unitary is that a unitary maps unit vectors to unit vectors. And so if every column wasn't a unit vector, then that wouldn't be possible. So because every column is a unit vector, well, we know that after the zeroing process is done, this element has to be 1. Okay? Now, also for a unitary, every row has to be a unit vector. And you can see that property as being a direct consequence of the fact that U dagger, equals identity. Because every column has to be a unit vector, well, in order for that to end up working out with this property, we also need to have that every row is a unit vector. And this means that we've actually kind of done more work than it might initially seem. Because every row has to be a unit vector, and this already is 1, the only choices that we have here, because the length of this row vector is 1 squared plus absolute value of d double prime squared plus absolute value of g double prime squared. Since that has to be equal to 1, and these are all positive numbers, we have to have that d double prime equals g double prime equals 0. So by zeroing the first row, using the unitary constraint, we have to have that d double prime equals g double prime equals 0. So doing the first row actually clears out the first column. So if we want to now build our unitary, our final unitary, all that we would have to do is we would have to do one more two-level unitary. With U equals E double prime, F double prime, H double prime over I double prime. Inverse. Because now we've reduced our problem to just apply just a two-dimensional subspace that isn't done directly. Now I could go through and do the exact same process and zero out the first column. It turns out that zeroing out the first column would do exactly what we need, and we'd only need one rotation. And that logical process is exactly the same thing as saying we apply the inverse, the transformation for it. So we apply this two-level unitary on the particular subspace, right? And the result is going to end up being that this will go to identity, 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 using the exact same reasoning. So everything considered, it took a grand total of 3 two-level rotations to make this work. Now, if we consider this in general, right, for an arbitrary matrix where we have U 0, 0 going all the way down to U 2 to the n minus 1, 0, then U 1, 0, going all the way down to U 2 to the n minus 1, 1, so on and so forth. Then you see what we have to do. In order to zero out the first two elements, we need one two-level to do this. And then the next stage involves zeroing out the next one. Everything considered, we need to do the zeroing process a grand total of 2 to the n minus 1 times. Now, once we've done that, then the first row also had to was automatically done. So now the next zeroing operations that we would have to do once we've done the first column would be zeroing out this one. In order to zero out this one, we have to do this, then that, then all the way down to the bottom. And we can see that there are 2 to the n minus 2 operations that we have to do. So everything considered, the number of two-level unitaries is equal to sum from j equals 1 going to 2 to the n minus 1 of 2 to the n minus j two-level unitaries. And this ends up scaling as order 2 to the 2n. Okay, so this scaling actually is pretty huge, right? And it scales quadratically with the length. But if you just consider the number of matrix elements that we have in here, We've got a total number of numbers that specify the unitary being 2 to the n rows by 2 to the n columns. Therefore, if we take a look at the total number of numbers that we have in here, we have 2 to the 2n numbers in total. And so if we've got 2 to the 2n numbers in total, then really we're going to need on that order of 2 to the 2n different parameterized unitaries just in order to be able to specify all of the information needed to describe this huge matrix. So the scaling of 2 to the 2n actually isn't really all that surprising, everything considered. It's just there's an immense number of different matrix elements that we have to program into the matrix using this technique. And so just to be clear, once we've got these three unitaries, we had, okay, I called them Wn, Wn minus 1, and Wn minus 2. This sequence of unitaries that I've described here is equal to, in that order, the final matrix that we wanted to build. A, B, C, D, E, F, G, H, I. Now, also, I should mention the problem of zeroing out the first column of a matrix is actually also equivalent to the problem of state preparation. So if you note, if we have a matrix that's of the form, let's say it's like A, B, C, D, E, F, G, H, I, and we want to act this on the zero state, which is equivalent to 1, 0, 0. Then in this case, that ends up giving us A, B, C. So if we wanted to be able to prepare a unitary that will transform 0 into an arbitrary state, all we need to do is find a unitary that has ABC in the first column. So this whole process of building an arbitrary unitary actually becomes a lot simpler for state preparation because all you have to do is build a unitary that has ABC, and then who cares what you get in the rest of this if you just care about state preparation. And so then the idea basically is that you want to then be able to find Wn minus 1 and Wn minus 2 in this case, such that this is equal to 1, 0, 0, and who cares what happens everywhere else. If you end up finding this, then this unitary ends up satisfying, well, Wn minus 2 dagger, Wn minus 1 dagger, Wn dagger acting on 0 has to be equal to A0 plus B1 plus C2, which is just, again, a Dirac version of writing that arbitrary vector at the top. So this is how you can actually also use this, not just to prepare an arbitrary unitary, but also to build an arbitrary quantum state. So this shows that using order 2 to the 2n, two-level unitaries, this ends up going to a, this allows us to build an arbitrary unitary. Now, we showed that in the last lecture, each two-level unitary needs order n gates taken from the gate set Hadamard, T, and C naught, using the fact that Toffoli can be built using order 1 T and H and C naught. So using those results, we have that each two-level unitary needs that, and therefore the total number of two-level gates we need from the set in order to be able to build an arbitrary unitary is order n 2 to the 2n. Okay, and this ends up proving, because of the fact that we can approximate any single qubit rotation within arbitrarily small error, we can do any two-level unitary within arbitrarily small error, and therefore we can implement any arbitrary unitary within arbitrary error using this number of operations. So this ends up showing that we can build anything we want on a quantum computer using a finite size gate set. The problem is this guy over here. It says if we want to do the transformation on n bits, we're going to need 2 to the 2n gate operations in general to be able to do this. And in fact, this cannot be substantially improved. So the quantum computers actually really struggle to do almost all generic unitary transformations. Our task in quantum computing is to find transformations such that one, U is cheap. And by cheap, what I mean is it requires order poly n gates, like a polynomial number rather than an exponential number of gates. And two, that U is useful. And so the next couple of lectures, we're going to be going in to some constructs that we have that we can find in order to find particular unitary transformations that we can do that are both cheap and really useful. And in fact, under some circumstances, modulo some reasonable assumptions can give huge advantages over ordinary computing. Thank you very much, and see you all next time.